Welcome to the Explainer. So, what could a satellite whizzing around the Earth possibly have in common with the engine in your car? Well, the answer is all about the physics of motion. Today, we're going to really break down the core ideas, work, energy, and power that literally make everything move. All right, here's the game plan. First up, we're going to challenge what you think work means. Then, we'll get into energy. Think of it as the currency of motion, and connect the two with a super important theorem. After that, we'll dive into different kinds of forces and finish up with power and, why all this actually governs, well, everything.
Okay, let's kick things off by talking about a word we all use constantly, work. But here's the thing. In physics, it has a super specific meaning, and it's probably not what you're thinking.
I mean, it feels like the definition of hard work, right? Your muscles are burning, you're sweating, you're exhausted. But believe it or not, according to the strict rules of physics, the answer is no. You haven't done any work at all. Let me explain why. So here's the absolute key. For work to happen in the world of physics, you need two things, no exceptions. One, you need a force. And two, that force has to actually move the object. It needs to cause a displacement. If that object doesn't move, it doesn't matter how hard you push or pull. From a physics standpoint, you've done zero work. Zilch.
And of course, there's a formula for it. It's simply force times the displacement times the cosine of the angle between them. Now, don't let the simplicity fool you. This equation is incredibly powerful because it's always valid. It works for any kind of motion, which is a huge deal.
That little cosine theta part of the formula, it's the secret sauce. It's what gives us three different flavors of work. You get positive work when your force is on the same team as the motion, like when you're pushing a box forward. You get negative work when your force is fighting against the motion, like friction trying to slow something down. And then the really interesting one, you get zero work when your force is at a right angle to the motion. Speaking of zero work, let's look at the classic example that everyone uses because it's just so perfect. A satellite orbiting the Earth. Okay, so you've got this massive force, right? Gravity is constantly yanking that satellite inward, preventing it from just flying off into the void. So the big question is Earth's gravity doing any work on that satellite? And the answer is a big, fat no. Here's why. Gravity pulls the satellite straight down toward the center of the Earth, but the satellite itself is moving forward, tangent to its circular path. So the force and the direction of motion are always at a perfect 90-degree angle to each other. And what's the cosine of 90 degrees? It's zero. So the work done is zero. This isn't just a cool trivia fact, it's the fundamental reason satellites can keep orbiting for decades without running out of gas.
All right, so we've got a handle on work. Now let's flip the coin and talk about its partner in crime, energy. You can't really understand one without the other.
What is energy, really? Well, the simplest way to think about it is as the capacity to do work. It's like having money in the bank. You don't have to spend it, but the money gives you the ability to buy things. In the same way, energy gives an object the ability to exert a force and make something move. It's the currency that makes the universe go round. Now, for our purposes, we're mostly talking about two main types of mechanical energy. You've got kinetic energy, which is the energy of motion. If it's moving, it has kinetic energy. Simple as that. Then you have potential energy, which is stored energy. It's energy an object has because of its position or configuration. Like a ball held up high has the potential to fall.
Okay, so on one hand, we have work, which is a process, an action. On the other, we have energy, which is a stored quantity, a capacity. So, how do we build the bridge that connects them?
Well, that bridge is a concept so fundamental, some have called it the father of all laws in physics. Why such a big title? Because a lot of rules in physics have a little asterisk next to them, They only work under certain conditions, but not this one. This rule is always true, no exceptions.
It's called the work-energy theorem, and it's so elegant. It says that the total work done on an object is exactly equal to the change in its kinetic energy. That's it. Do positive work on something, you increase its kinetic energy. It speeds up. Do negative work, you decrease its kinetic energy. It slows down. It's a perfect one-to-one relationship.
Let's make this real. Imagine a 20-kilogram object is zipping along at 5 meters per second, and then it slows down to 2. Now, using this theorem, we can figure out exactly how much work was done to slow it down, even if we have no idea what the force was or how far it traveled. All we have to do is calculate its kinetic energy at the start and its kinetic energy at the end. The difference is the work done. In this case, it's negative 210 joules, which tells us some force, probably friction, did work to pull that much energy out of the system.
But, you know, things get a little more complicated because not all forces are created equal. How a force interacts with energy is a really big deal, and it's key to understanding where energy sometimes seems to vanish.
Okay, so we have two types of forces. First, there are conservative forces, like gravity. Think of them as a savings account. When you lift a book, you do work against gravity, and that work gets stored as potential energy. You can get it all back when you drop the book. The path doesn't matter. Then, there are non-conservative forces, like friction. These are more like a tax. The work you do against friction is lost from the system, usually as heat. It's gone. And with these forces, the path you take matters a lot. A longer path means more energy lost.
And this is exactly why we called the work-energy theorem the father law. You've probably heard of the law of conservation of energy, right? Well, that's kind of like the sun. It's a special case that only holds true in a perfect world where there are no non-conservative forces, no friction, no air resistance. The work-energy theorem? It doesn't care. It works in the real world with all its messy forces every single time.
Okay, so we've got work and we've got energy. But there's one more piece to this puzzle. It's not just about if you do the work, but also how fast you do it. And that, my friends, is power.
Power is all about the rate. It's the measure of how quickly work gets done or energy gets transferred. We measure it in watts, and 1 watt is super simple. It's just 1 joule of energy being used every single second.
Think about it this way. Let's say two people climb the same rope. They both weigh the same, they climb to the same height, so they have done the exact same amount of work against gravity. But if one person scrambles up in 20 seconds and the other takes almost a minute, the first person is way more powerful. They did the same job, just a whole lot faster. All right, let's bring it all home. Let's look at the big picture and see why these 3 ideas, work, energy, and power, are just so essential.
So, here's the big takeaway. Work, energy, and power aren't just abstract ideas for an exam. They are a toolkit. They give us an incredibly powerful way to analyze the world. Instead of getting bogged down trying to calculate every single force acting on something, we can just look at its energy at the beginning and at the end. It's like doing accounting for motion, and often it's a much simpler way to get the right answer. And that leaves us with one final, fascinating question to ponder. We said that friction makes mechanical energy disappear. But we also know that energy can't be created or destroyed, right? It only changes form. So, if the work done by friction removes energy from the motion of an object, where does that energy actually go? The answer to that question, well, that's where things get really interesting. And